Morning, guys. I hope you are all doing fine. Any questions before we start discussing the new topic, the line segment intersection? Rahman, could you please tell Canberk that he can log out and then log in once again? I admin him, but he cannot, I think, log into Zoom. Any questions, guys? Okay, today we will start discussing line segment intersection. And as you see on this slide, we have many lines. And in this topic, we are going to learn a special algorithm, a plane sweep algorithm. With the help of it, we will be able to determine all the intersections of these lines in a shorter time than expected. And our algorithm will depend on, the time complexity will depend on the number of intersections we have on the table. So let's start from the basics, from the fundamentals. How do we determine the intersection of these two lines? Any comment, guys, how we can proceed? Can talk or write. It's a very simple equate their equation. So we need to first have their equation then, right? These are some simpler lines. I can write that. This is why it's not writing. Sorry. Yes. This is y is equal to x, obviously, and the other one is y is equal to minus x and some value. Assume that this is 4. So as your friend pointed out, then what we do, we use this expression into the other one, and then things are going to be simplified. Oops. Plus 4. So x will become equal to 2. And since this is y is equal to x line, then y will also be equal to 2. And this is the coordinate of the intersection point. So this is how we proceed. If you have the equations of the lines, you can put one into the other and try to determine the intersecting point. But sometimes they may not be intersecting. So what is that case? Can anyone tell me any information about that case? If the lines are not intersecting, then what type of property should they have? Since let's say this is one of them, this is another, probably they are going to be intersecting somewhere downwards. So what should be the, yes, one answer. If they are parallel, then we cannot say that there will be an intersection. This is the only thing about the intersection of lines. But what about the line segments? How can we determine the intersection point of line segments? Can we use the similar idea, but right now we don't have the equation. Instead, what we have, the coordinates. Let's say this is the starting point. This is the end point. And then we have another starting point. So how we are going to compute this intersection, if there is any? Oops. Why are written like this? This should be 1, obviously, and this should be x2. Okay. And then we have x3 and y3. An idea, guys, how we are going to determine the intersection? So you don't know how to determine it, okay? This is your kind of homework. Make sure that you know how to determine the intersection of any two line segments. And obviously, as you see, these line segments are intersecting. We have an intersection. But what about these? Let me draw two other line segments. What about these? Again, they have starting and ending points, but right now, as you see, they do not intersect. So if you have a kind of an equation, then you will be actually spending your time uselessly. Why is that? Since obviously they do not intersect, and you shouldn't do any computation and simply say that they're not intersecting, right? But how can you do that? What about these, for instance? Do I need to do any computation to check whether these two lines are intersecting? So one of you say that you should find equations, but do we need to find equations? If they are not intersecting, why we should spend our time? If they are intersecting, if you are sure for that, then you may find the equations and then try to do the same what we have done in the previous slide. But if they are not intersecting, if that's clear, then it's not worth actually finding the equations. What is the idea? You may check, for instance, if you look at this couple, you may check their y and x intervals. So if you look at the x interval, this is the x interval of the first one. This is the second one, let's say. And they are intersecting, right? They have overlapping x values. But what about y intervals? This is the y interval for the bottom one. And we have another y interval here. And obviously, without any computation, we can say that their y intervals are not overlapping. They're not intersecting. So I can simply say that without any computation, these two line segments cannot intersect since their y intervals are not overlapping. But if you look at this pair, assume that this is a bit here around, let's say. So their y intervals are overlapping, right? This is the second y interval, and we have an overlap here. This is the overlap. And for the x, again, we have an overlap. So this might be a potential intersection. So we need to do actually some calculations. We cannot say by simply looking at the intervals whether these two line segments are intersecting or not. So we need to do some computation. But for the one on the right-hand side, without any computation, we can easily say that they're not intersecting since their y intervals are not overlapping. So let's have a look at our problem. The problem we are going to work on in this topic. The problem is we have a set of enclosed segments in the plane. So we have, let's say, the first line, second line, third line, and we have up to n line segments, or they are called as closed segments in the plane. And our aim is to find actually all these intersection points among all the segments in the given set S. So there are n line segments in this set, and we are going to determine the number of the intersections, their coordinates, and how many of them there are on the table or on the plane. So what do you think? What is the simplest way? The first thing actually come to your mind if you are given such many line segments, and if you are to write an, let's say, script, in Python, let's say, how we are going to determine whether you have some intersections or not, or if you have intersections, how many of them there are, and what are their coordinates. How we should proceed if you just want to do a simple implementation. No answers, guys? So I'm waiting at least for one answer. So how we can determine the intersections of all of these closed segments?
Like with using brute force, we can check all the lines to pairs. But
Yes, we have, so intersection should be, as you know, in between two line segments, right? So in special cases, it might be between like this one, but it's a very rare case. You may have such line segments. 3 of them might be intersecting at the point, but this is a very rare case, and we call these cases degenerate cases, and our focus will not be on these. But for others, we'll always have pairs, right? And that one might be also intersecting with another one. So what we need to do is simply, we may have 2 for loops, 2 nested loops, and try to determine all these intersections. And they should be all running up to n, since we need to check all the pairs in this given set S. Otherwise, we may miss some of the intersections. So we should be checking all the possibilities, and this is done with the help of a nested loop. Okay, and this is what we call as a brute force method. This takes lots of time. We don't consider any property of the plane, any property of the intersections. Our aim is to find all the intersection points. Time is not a concern for us right now. Our main aim is to find all the intersection points, and this approach simply guarantees that since you are checking all the possibilities, you should be able to actually find all these intersection points. And this is, as I mentioned, called as a brute force method, a very simple and time-consuming method. And since we are using 2 for loops inside each other, so that's why it will take quadratic time. And if you have huge number of, let's say, line segments on your plane, then this might be an highly time-consuming algorithm, and you may need to maybe wait for hours, for a day, even if you have some thousands of lines, millions of lines. But we will try to find a better way. We will look for some other algorithms which are output sensitive, which are sensitive to the number of intersections. Now we will go into the details of this plane sweep algorithm and try to find a better algorithm with less time complexity. So usually, actually, on the plane, you have many line segments, but most of them do not intersect with each other. Just they intersect with fews, maybe with a single line segment or a maximum 2. So in real life, actually, in practice, this number should be much less than quadratic in time. So our aim is to find a faster algorithm so that its time complexity will be less than quadratic, and our algorithm will depend on the number of intersection points. If you have less number of intersection points on your plane, then your algorithm should take less time. If you look at the brute force algorithm, regardless of the intersection points, it will always take the same time. So this is what we are going to change actually. Our algorithm will depend not on the number of segments, not only, but it will also depend on the number of intersection points. And we call these algorithms as output sensitive algorithms. And in our problem. Output is the intersection. So we can say that the new algorithm we are going to work on is called as an intersection sensitive algorithm. But how we are going to do that? How can we actually avoid testing all these pairs? As we have discussed in the beginning, we may check some intervals. If they are not, let's say, related to each other, if one is here, if the other one is at the bottom, then we don't need to spend time on the computation of their intersection. Since we know that they're not intersecting, so we should simply pass it, and we need to focus on other candidates. So let's have a look at this one. Here you see we have how many? 5 line segments. And as we see, there is no intersection. But if you follow the brute force method, we need to check all the pairs. Even though they are not intersecting, we should do this checking. But let's focus on the Y interval here. Do we have any overlapping intervals? Yes, this one is here, for instance. So this is a possible candidate. Another one here. So we may do some computation on the first couple and the last couple, but still we know that obviously by looking at this plane, they're not intersecting, and we may further focus on their x intervals, right? But we will be first going into the discussions with the y interval, and then we will focus on the x interval. So how we are going to proceed? We will actually kind of have an, let me draw it here, a virtual line, a fictitious line, which will be moving downwards. And while going downwards, this will be scanning the whole plane, and on the way, actually on the fly, we will try to determine this intersection points. Since, let's have a look at here, while this line, this virtual line is at this point, we can say that there are 2 intersecting line segments with this virtual line, which means that since they are neighbors, they might be actually intersecting at some point of the plane. So that will be actually the main scheme we are going to follow. We will be using an imaginary line. It will be sweeping the plane downwards, and while we are going downwards, we will do some checks. And depending on the checks, we will update some data structures and try to do some computation, and finally determine all these intersections. So if, as it's written here, we only need to do computation for the pairs which have overlaps in y-axis. For instance, if you come here, we don't have any intersecting line. Here we have a single line, so there is no need to check. But here again, we have 2 line segments and their y intervals are overlapping. And we determine this overlap by a virtual line moving from up to down. Yeah, that's what I mentioned. We will have a sweeping line, and we call this line as an L. And obviously, it will start from above all those line segments, but you can do also the reverse. You may start from the bottom and go upwards, but things will be the same. Just you need to update some comments, let's say in your implementation or in your algorithm. So what we are going to do while going through this plane, we will always keep track of, this is the important part, we will be keeping track of all the segments intersecting this imaginary line. As I have shown you in the previous slide, this is the most important information we should be always updating. And once you have that information, then you may further do some calculations and try to determine if you have any intersecting lines or not. And this type of algorithms are called as plane sweep algorithm in config design or computational geometry. And this line we are working on is called as sweep line. And this is actually drawn here, as you see. We have 4 line segments. This is our imaginary line, the sweep line. This is sweep line. Okay. And we will start from the top. This will be the kind of starting point, and we will be going downwards. As we go downwards, you'll see that there are some event points. And these event points are important since at these event points, we'll stop and try to do some computation. For instance, if you look at here, just consider this point, this location of the imaginary line. At this point, our sweep line meets an end point. This is the end point, or we can say that upper end point, and these ones are lower end point. I can write it here. This is upper end point. This is the terminology we are going to use in this topic, upper end point. And obviously, the bottom ones are called as lower end point. This is lower. So once you meet such event points, what you're going to do, you're going to update some data structures in your algorithms and maybe do some computations. Since if this is an upper end point, then that means we have a new line in our, let's say, plane. So what we are going to do, we need to do some checks with the neighbors. So if you look at here, the neighbor of this new line is the one on the right here. So this is a potential maybe intersection. It's an indication of an intersection. So what we do, we check whether this line segment is intersecting with the right one or not. And we do the computation right at this point. And at the lower end points, again, these are kind of event points. You'll see that we have 3 types of event points: upper end points, lower end points, and the intersection points are event points. And at each event point, we need to do some computation and try to find some new intersecting points. In questions, guys, we will be going into details. Make sure that you are with me and you understand the fundamentals of this approach. Otherwise, the upcoming slides might be more complicated.
Hocam, I have a question.
Yep.
How often we draw sweep line? Every time we see an event point or another?
Yes, we don't actually do any computation in between. For instance, assume that this is another level for the sweep line. So in between these 2 event points, actually, we don't need to do any computation. We will go into details, but you can keep in mind that the event points are the critical ones, and we need to stop at these event points, do some computation, and then continue with the next event point. But in between, it's not important, and we know that in these in between these event points, we don't have an intersection. So our main focus will be on the event points, and I said there are 3 event points: upper end points, lower end points, and intersection points. So once you come up with any of these, then you should stop and take action according to the type of event point you have. But we are not drawing, obviously, this is an imaginary line. We will do some computation, but graphically, we are not going to see a sweep line. Any other questions, guys? Okay, so as I mentioned, the intersecting line segments with the sweeping line is quite important. So we should be keeping track of these intersecting segments with the sweep line. So that we need to have a kind of a data structure. And in that data structure, we should be keeping the line segments who are intersecting with the sweeping line at that, let's say, instant. So if you look at this point, assume that this is the first line segment, second, third, and the fourth. So which of these are intersecting with the sweep line? The first, second, and the third one, right? So I may have a kind of a data structure, maybe. This is not actually correct, but assume that this is the kind of way we are storing the intersecting lines, the segments who are intersecting with the sweep line. But at that point, let me draw another one here. What will be the status now? It is 2, 3, and 4, right? I'm sorry, actually, this one, we also need to have 4 here. Yes. But above this line, here the status of the sweep line is a bit different. 1, 2, and 4. Okay. And at the ends, let's say you have the sweep line here, then the status will be simply 2, which means that we only have the second line segment intersecting with the sweep line. So this information is highly important, and we need to keep this status all the time updated. Otherwise, our algorithm will fail. Yes, as we discussed already this issue, our status will be changing all the time, but not continuously. In between the endpoints, it's always the same, but once you come up with an event point, its content will be modified. This is the same thing I mentioned. At the event points, there might be updates on the status, and these event points are usually the endpoints of the segments and the intersection of the line segments. So what we do at the event points, at the lower and upper endpoints, the status of the sweep line should be updated. The intersecting line segments with the sweep line should be modified, and you should have an updated status data structure. And another thing we need to do at these event points is to check whether we have any intersection or not. So if the event point is the upper end point, let me draw it here. So that this is our line segment. And if you have such a sweeping line, and we say that if the event point is the upper end point of a line segment, then that means obviously a new segment is going to be added to the status. So what we are going to do, assume that initially we have 1, 2, 3, and we might be adding another line segment into our status. 1, 2, let's say 4, and 3. So at upper end points, we need to add a line segment into our status. Any questions, guys, up to this point? Make sure that you are with me, since the upcoming slides will be more complicated.
Hocam,
Yes,
are
Harun?
we doing sweep with for loop and checking with if conditions for all segments?
No, we don't have actually kind of a for loop for the whole plane. We are simply checking the y values. We'll go into details, but we don't have a proper for loop. We're going like this. So the ones actually having higher y values will be checked first, and then the other ones will be checked later. So we don't have a proper loop in this algorithm. So then what we are going to do, if you add a new line segment into your status, then what you should do is to test your line segment with the other line segments in the sweeping line. Since it means that if you are adding a new line, we said that initially there is just 3 of them. And once you add a new line segment into it, let's have this one. So this is the new line we just added. And then what we should do, we should check whether this fourth line segment is intersecting with the second one, or intersecting with the third one, or intersecting with the first one. This is what we should do at the event points and try to find whether there are any intersecting points with the fourth segment or not. And let's focus on the lower end point. Things are similar, but this time lower end point means that a line segment is actually removed from our data structure. Assume that this is the second one, okay? The second item here, second line segment. Then how our status will be? This will be the updated status, right? If this is the second line segment, and if our sweeping line is right at its lower end point, then we should be actually removing this line segment from our status data structure. So this is what we do. If you remove the second one, then we are left with 1, 4, and 3, which means that, again, our status is updated and we need to do some more checks. Again, we will check all these pairs. This one with 4 and 4 with 3, and we have another option. We need to check the first one with the third one. So these are the checks actually we need to do if you have any updates on the status data structure. But this is not enough actually. Why not enough? Since again, it's quite time consuming. Why do you think is that? Why this algorithm is not finished yet, and why I say that it's still time consuming?
We have to sort the points in increase or decreasing Y order, maybe.
Y order or X order?
I said Y because we are going down on Y coordinate system when starting with the maximum Y and continue with the lower one.
But this is the thing actually we should do at the beginning of the algorithm, right? If you have this order at the beginning, then you can proceed with what we have discussed up to now. So there are some questions. How do we know the intersection points before sweeping them? We don't know the intersection points, and we try to determine them while we are going downwards. And for instance, we may determine them while we perform these checks. Up to this point, I'm not sure whether we have any intersections or not, but once you do checks, then you may say that, yes, there is an intersection between the fourth and the third line segments. This is the point actually we determine the intersection points. And there's an answer to my question. I said that this algorithm right now is not enough in terms of time complexity or time consumption. We are still consuming more time. We have unnecessary computations. And one of your friends says that because we are checking almost every Y point. Actually, it's not that we are, the problem is that if you focus on here, we are checking all the pairs and the status. Why do we need to do them? We need to we may do some checks with the neighbors. For instance, the first one might be far away on the x-axis. So it's not in our, let's say, scope of intersection. We don't need to do computation calculation on between the first and the fourth one. Instead, we may just focus on the neighbors, left and right neighbors, and then continue. If we do it, then our time complexity will be decreasing a lot and we'll be more successful. Yes, this is Ahmet mentioned also similar things. We need to also consider the X values. Otherwise, our time complexity will be very close to quadratic in time. Oops. Yes. So if you consider this one, for instance, we have many lines, and let me draw in fixtures in sweeping line here. As you see, there are many line segments. Actually, all of them are intersecting with this sweeping line, right? So if you have a new line segment, let's say that this is an event point, an upper end point, and we have a new line segment going into our status data structure, or the status of the sweeping line is just updated. According to the previous discussions, then we need to check whether this line segment is intersecting with all the others in this status, right? But obviously, as you see, this is a highly time-consuming task. Their x values are different, even not close to the x values of our line segment. So why we are spending time for the checks between the new line segments and the ones on this, let's say, left-hand side of our plane? So the thing is that, as I mentioned before, we should only be checking actually the neighbors. So this is the neighbor. It only has a left neighbor. It doesn't have any right neighbor. So we should do the check just with the left one. And with this approach, we will be decreasing the time spent on the checks, and the overall time complexity, the overall time spent will be decreased. So if you look at the previous slide, obviously our algorithm right now is not output sensitive, since we are checking with all the possibilities, even though they are not intersecting with the new line segments. So what we should do, we should be doing some kind of an order from left to right, as we have done in some primitive examples. So we will be only considering the closer ones to the event points. So as written here, we will be testing only the adjacent ones, or the neighbor ones. So neighborhood is important. We will only be testing the segments which are actually neighbors, according to the horizontal ordering, which depends on their x values. So this is an important issue. While our sweep line is going downwards, then a segment actually become adjacent to other segments, which is going to be tested, right? So let's have a look at here. At this point, we only have a single line segment, right? But once your sweeping line is around this point, I'm sorry, then we have a new line segment, and at that event point, we should be checking whether this one SL is intersecting with SK. So once you do that check, you will see that there is an intersection, and you should store this intersecting point into somewhere so that you will later do some processing on it. And then once you come to, let's say, this endpoint, again, you need to do some check between SJ and what is the neighbor right now here? SL. So your first check of SJ is in between SL, not between SJ and SK. But if you assume that this one is, or let me come to this point. Let me draw another one here. Yes, after this intersection point, the status of our sweeping line is modified. Since initially, or let me draw another one upper, and I will order these line segments from left to right. So SJ is first, and then we have SL, and then SK, and finally SN, right? This is the status we have here. And then at the intersection point, things are a bit different. But after the intersection point, our status is updated. Now you see that this is SJ, SK, SL, and SM. So we replace the order of SK and SL, right? After this intersection point. So that's why the intersection points are also important for us. And that's why we will be considering them as event points. And at this intersection event points, again, our status will be updated and we need to do some more checks. So we said that we should be only considering neighbors. So in the previous case, we are only checking SJ with SL, right? Since they are neighbors. But after the intersection point, we have a new neighbor of SJ. So we need to do some check between SJ and SK right now. And also we need to do some check between, I'm sorry, this should be S obviously, SL and SM, since they are new neighbors. Before this intersection point or before that event point, they were not neighbors, so we didn't check them. But after the intersecting point, we have a new neighborhood, so you should be checking whether there's an intersection between SL and SM. Any questions, guys? So obviously our status will be corresponding to the order sequence of this intersecting segments, as you see here. So this is not new information for us. And the important thing is that we should always be keeping track of, keep updating this status data structures. If you don't update them, then while going downwards, you may not be able to find all the intersections successfully. Any questions, guys? So as I mentioned, the status line also changes at the intersection points, not only at event points. So once you come up with an intersection point, again, you need to do some tests between the new neighborhoods. So the question right now is, instead of checking all the pairs in the status, what we are doing right now, we are only checking the neighbors, right? The left and the right neighbors of the new line segment, or if you remove one line segment, then you will have another neighborhood. So we should do another check. So we decrease the number of checks, number of pairs. But the thing is that, do we still find all the intersections? Since we are not checking all the pairs, can we say that with this approach, all the intersection points are found or not? What do you think? So Ahmed, do you have another question? I think from the previous slide, let me go back. So you say, do we check SK and SL again? No, since they are already checked and they were neighbors in the previous, or at the upper region of the, let me draw it here. They were neighbors here, so they should have checked already. So we don't need to do any other check once again, since they are again neighbors. Just their order is modified. So the question is, by following such a scheme, can we find all the intersections by only checking the neighbors instead of the whole, let's say, pairs? Or do we need to do any more calculations? Idea, guys? and we are assuming that there is no horizontal segment. So which means that if that is a sweeping line, we don't have any segments which will be fully overlapping with the line, sweeping line. So this is our assumption. It's some kind of an, again, degenerate case. So what do you think? Can we find all these intersections? Assuming that there is no horizontal line and there is no three segments actually meeting at a common point. So we can actually say yes, we can determine all the intersections if you are just checking the pairs, checking the neighbors. Why is that? Since we know that if you have an intersection, you should have actually find that intersection somewhere above the sweeping line. So this is our first lemma. As you know, the lemmas are some small, let's say, theorems. So it says that we have two line segments, Si and Sj. Obviously, they should be non-horizontal. They shouldn't be horizontal. And we are assuming that the interiors are intersecting in a single point P here, right? And we are assuming that there is no third or fourth, let's say, line segments passing through this intersection point P. Okay, then we can say that there is an event point of P above P, where as I and Sj become adjacent and they should be tested for intersection. What is that actually point, event point? This is actually the event point. The upper end point of Sj will be embedded into the status structure, embedded into the status of the sweeping line, and at that event point, we should do a check between Si and Sj, since they are neighbors at that point. So we should be doing that test right at upper end point, and we should have found that there's an intersection between these two line segments, and this is P. And this covers actually our first lemma. If you have two line segments intersecting with each other, and if they're not horizontal, and there is no third or fourth line segments going through the same intersection point, then we can say that these two line segments must be neighbors at some point above the intersecting point. So by this lemma, I can say that we can find all these intersections by only checking the neighbors. We don't need to check all the, let's say, line segments in the status. Checking the neighbors is fine, and you don't need to do more computation. Okay, guys, this is all for today. Any questions you have? If not, we can call it a day. And
Teacher, can I ask something?
Sure, Mithat.
Like we said that we are checking every neighbors, like when we go down, when we're sweeping the lines, we are checking every neighbor. But for example, one of the lines is at the left side and one of the lines at the right side, but they are intersecting way down. Like further we go into the algorithm, are they going to be as neighbors?
Yeah, we are assuming that, and they should be neighbors at some point downwards. So that's why we don't check them at the corresponding point, but we are going to check them at downwards. So we only do checks once they are neighbors. And that is enough, according to this lemma, that is enough. And we will also have some detailed examples. You will see that they should be checked once you move your sweeping line downwards. Okay. Any questions, guys? If no questions, then I'm closing this session and see you on Tuesday. And I forgot to tell that I will send you an email. I will extend the deadline of the second mini project by 1 or 2 days since we are still discussing. So I will give you more time and you will be able to do the, I think, 7th question in a much easier way. Okay. Have a nice day, guys. See you next week.